Morning, everybody. Morning. Goal for today, finish up chapter 16, and I think we'll make it. Assuming this old man doesn't, tell stories or something like that. I'm old. Feeling it every day. Okay, so intensity of sound. We are talking about volume now. And we're going to, how do you measure volume? How do you characterize it? All that kind of stuff. So let's just, the equation I'm about to give you applies for any intensity. This is just the generic intensity, definition. Technically, it would be a triple equal sign, but we'll just go with the standard, okay? Take the power and divide it by area. So this applies to sound waves. It applies to light waves. It applies to, any power delivered to any amount of area, you can calculate the intensity. So the intensity of sunlight striking the surface of the earth, right, would be the power that comes down per, say, square meter of surface area. So when it comes to sound specifically, we got to talk about the area over which the power of a sound wave is spread. And we got to back up a little bit to that concept and idea about this three-dimensional waves coming out of my mouth, coming to you and spreading out as spheres, right? The waves coming out sort of spherical in all directions into 3D space. So what we're going to do for sound, can't spell, sound, okay? Our intensity will be still the power divided by the surface area of a sphere. And of course, that's something you just know right off the top of your head, right? You've got that one memorized? Oh, I'm impressed. Yeah, that's it. Yeah. Because all of these stupid things are so close to each other, right? Is it pi r squared? Is it 2 pi r? Is it 4 pi r squared? Is it 4/3 pi r cubed? Right? But yeah, that's the surface area of the sphere. So for sounds, specifically, okay, we will use this all the time. Because what we're doing is we're modeling all sounds, whether it's my voice, whether it's the door closing, whether it's a speaker coming out of your phone. We're modeling it as a point source. It's a point in space that is then spreading out. This gets a little bit, well, not a little bit, it gets a lot harder when we start talking about say surround sound systems. You got 3.1, 5.1, 7.1 channels, right? The individual speakers can be thought of as point sources, but then sometimes you get sound bars that are doing all of this weird waveforming to make it sound like it's bigger than it is. But we'll stick with the simple point sources of sound. The thing that you need to understand about intensity, notice that it falls off as an inverse square of distance. So if I'm standing here in the front of the room, the amount of power that I put into the sound, the energy per time, okay, that usually is fixed for a given volume. I can go really quiet, you can barely, right? I've lowered the power there, right? So of course the intensity went down. But if I use my standard teacher voice and I'm projecting, so I'm trying to fill the room so that the people in the nosebleed section, how you doing back there? Doing good? Still hear me? Yeah? Okay. So let's talk about, though, okay, what happens for people that are 1 meter away from me versus people that are 4 meters away from me, right? We've quadrupled the distance r, right? The distance away from the point of sound. And it goes as 1 over r squared. We've kind of done this before. We did it with gravity. Nature loves a 1 over r squared law. Okay, it's just kind of built into the fabric of the cosmos. So for people sitting here in the front, they hear however intense they hear it 1 meter away. But how much lower is the sound for the people in the back row? If they're 4 times as far away, it goes as squared, inverse squared. So inverse means it goes down. It's 1/16 as strong. So people up here in the front are going deaf, while people in the back are barely hearing me, something like that. Well, it turns out human ears and our brains and the physics of all those connected systems they're able to capture quite a large range of sound intensity. Okay, so that range. So we talk about a reference intensity. This is the intensity, I not, that is the threshold of human hearing. Now, of course, dogs and birds and other things have different abilities to hear even fainter sounds than we can. But we'll reference this all to people, human beings, okay? And the lowest intensity that our ears can perceive, normal human ears, is 1 times 10 to the minus 12 watts per square meter. Remember, power is in watts and area is in square meters. So that's the lowest. What does that sound like? It's really hard to describe sounds with words, first of all. Second of all, it's even worse to try to indicate the threshold of human hearing, because so much of our environment, just stop and listen for a second. Do you hear the fans going in the projectors? And maybe some of the cars that were outside and different, right? Okay. We sit in a soundscape, right, that is more or less constant, right? Background levels of noise. Again, depending on how close to the street we are, but even in a room that's supposed to be quiet, right? There's white noise going on, stuff like that. So I asked a acoustical physicist one time, can you describe to me what the threshold of hearing is, right? So I could tell my students what it is. And she said, okay, this is what it is. Because she's measured it, believe it or not. Imagine you are in a forest and there's nobody around. And I said, okay, is this a joke? Is this going to end in some kind of tree falls and does anybody hear it? All that kind of stuff, right? She's like, no, but I do have a good joke along those lines, right? I think, what was her joke? She said, this is very sexist. If a man is alone in a forest and there's no women around, is he still wrong? Fair. That was fair. That was fair. Anyway, she said, imagine being in a forest alone, away from people and traffic. You're in the woods, okay? And the bears aren't making any noise, okay? And there's no wind, so you're not hearing the rustle of leaves or anything. It's just perfectly still. And let's say a leaf falls off of a tree, right? Flutters down and strikes the forest floor about 1 meter away from your ear. The sound that light leaf makes as it hits the forest floor 1 meter from your ear is the threshold of human hearing. And I thought that was a pretty good visualization. Now, is it going to happen? Probably not, right? Not unless you are super lucky, right? In my book. Some people get terrified by being alone like that. It's what I seek, right? So, but that's sort of the lowest intensity sound that our ears go, oh, something happened. There was a sound there, right? Okay. On the other end of that, is there an upper limit to the intensity or loudness of a sound where it gets so loud that we can't hear it anymore? Hopefully you've never experienced this, because if you did, your ears would start bleeding. Okay, so there isn't an upper limit to our ability to hear, an intensity, but there are limits to the actual structures in our heads, and they can break, okay, when they are exposed to certain limits of sound. So we don't like to talk about the limit where you're just basically destroying people's hearing. Instead, we define something even better, called the threshold of pain. And you have to say it that way. You can't. Threshold of pain is 1 watt per square meter. If your ears are exposed to 1 watt per square meter sort of suddenly, right? You weren't expecting it. Then you would very likely have an automatic response of like a duck and cover, or you would put your hands over your ears and kind of crouch down. Your flight or fight response would kick in. The adrenaline would start surging. Your brain goes, too loud, something wrong, fix it. Okay? And there's a lot of sort of reactions to that are independent of culture. It's just the human body going, I got to fix it. Okay? This is routinely a level that can be surpassed at most music concerts, especially modern music concerts. Okay, my wife used to play in a band and orchestra, and she would have to wear ear protection because the trumpets were right behind her. Right, so the audience members were fine, but her hearing was threatened, right, because of the trumpets sitting right. And nowadays they'll put actually plexiglass shields in front of the trumpets, because trumpets are annoying anyway. You just put them in a box, right? But like, it's just, I always wanted to play trumpet. They made me play clarinet instead. So the idea there is a point where you can be exposed where you will hurt. Now, if the rock concert goes loud for long, right, above 120, like, you can have sustained hearing loss from that. Okay, and so it's not uncommon to be next to the speakers and be exceeding this threshold of pain. And if you've been exposed to it for a long time, your brain might go, oh, it's normal, and doesn't hurt anymore, and you now can't hear anybody unless they're shouting at you. Okay, does anybody see any problem with the numbers on the screen? This constitutes the range of human hearing from the lowest sound up to where people go, ow, that hurts. Anybody see any problem with the numbers? No? Just going to accept them for what they are? They're not inaccurate, they're not incorrect. But there is a problem. No, still don't see it? What's the difference between the threshold of hearing and the threshold of pain? 1 trillion times difference. Do you see it? 10 to the minus 12. That is 1/1 trillionth of a watt per square meter, all the way up to 1 watt per square meter. The power of 10 to the 12 difference, right, between these two sounds. So that scientific term for this is, that's a huge difference, right? Like that's big. And so to come to grips with it, unfortunately, we're going to have to pull something out of the mathematical toolbox that is designed for handling big differences. And it's called the logarithmic scale. Sorry. It's the way that all sound is measured, so we got to deal with it. So let's deal with it. Okay? What we do is we do a kind of unit conversion from watts to square meters into something called decibels. And the decibel isn't so much like a conversion factor, right? 3.281 feet equals 1 meter or something like that. It's more of a conversion equation. Like, it's a formula you have to use to be able to go back and forth between the units. And here is the equation. The sound intensity in decibels. We use the symbol beta for this, okay? The symbol's beta, but the unit is dB, okay? Is equal to 10 log intensity being measured divided by reference intensity, where that reference intensity is the threshold of human hearing. This is log base 10. That's the good news, okay? But this is the equation you use to be able to find the sound level in decibels if you know the sound intensity in watts per square meter. To go backwards from this, to reverse this, like if we are given decibels and we need to find it in watts per square meter, we've got to figure that out. So let's go figure that out. What we want to do is we want to solve this for I. Okay? We want to be able to find the intensity in watts per square meter if we know the decibels. So how do we get I out of this equation? By the way, you've already done this mostly. Lab number 1, question number 3, part, I can't remember if it was B or C or D. You used logarithms, and it was in this form. Okay, so I'll help you out. Let's clean this up. First thing you do is get the logarithm by itself on one side. Okay, so I just divided both sides by 10, right? And then how do you get rid of a log? You raise it as a power of 10. And 10 to the log of something is, what's 10 to the log of something? It's something. The 10 to the log of, like the 10 to the and the log cancel each other out. You don't need to worry about this too much because once we have this down, I'm going to put a box around it, and that's the one you're going to use. Okay? So what does this tell us right here? It tells us that the intensity in watts per square meter is equal to the reference intensity times 10 to the decibel number divided by 10. And there's your way of getting those two red things in the box on the right-hand side. Those are your conversion formulas for converting between decibels and watts per square meter. Decibels, beta being measured in decibels, intensity I in watts per square meter. And the reason we have to go back and forth is, again, because this is the way acoustics works and all of their math is based on it. But we have to go back and forth also because when it comes to overlapping sound intensities and figuring out like what overall sound intensity is, never, ever add decibels. If you have a 50 decibel sound and a 60 decibel sound and you want to find the total intensity, it's not 110. Okay? It just isn't. Okay? And we're going to do some examples of this. Never, ever add decibels. Decibels are built on a logarithmic scale, and logarithmic addition doesn't work the way you think it does. And so our process to be safe is we will always, when we're adding sounds together, we will always add them together in units of watts per square meter, because those are linear units, and they add together just very nicely. And then we'll convert back to decibels. So we'll end up converting back and forth between decibels and watts per square meter like kind of constantly all the time. Okay? So these are the equations. Let's just kind of outline this for you. Okay? Just give you some idea of what why this decibel scale kind of works. So if we go and we look at the equation for the threshold of hearing, right? We come up here and we say, okay, right? I want to find the decibels for the threshold of hearing. And we put I naught into here. What is I naught divided by I naught? It's 1, isn't it? What's the log base 10 of 1? Does anybody remember properties of logarithms? This was a special one. It's 0. Log base 1, log base 10 of 1 is 0. In other words, it's asking what power of 10 will give you the number 1, right? 10 to the 0 is 1, right? So anyway, so 0 decibels corresponds to the threshold of hearing. So on the decibel scale, the lowest sound that the human ear can perceive is 0 decibels. And then everything scales logarithmically from there. The threshold of pain, right, at 120, where they say siren or rock concert, okay? Notice it's 120. So if we go back to the equation over here, if I put 1 watt per square meter and I'm dividing by 10 to the minus 12 watts per square meter, what's 1 over 10 to the minus 12? What's 1 over 10 to the, that was not a good color to pick. What's 1 over 10 to the minus 12? It's 10 to the 12, isn't it? Okay. And now you take the log base 10 of 10 to the 12. log of 10 to the 12 is 12. Like it strips out the exponent of 10, okay? And then we multiply by 10 to get 120. So that's what the logarithmic scale is doing. It's taking really big differences in watts per square meter and making those differences smaller. So we go from 0 as the threshold of hearing all the way up to the threshold of pain as 120, instead of having to like write down 1 trillion, put down 11 zeros after your number, all that kind of stuff. So that's what's going on, okay? So what this also kind of comes out, and human brains really don't like logarithmic scales. Let me see if I can't like explain that to you, okay? So let's take a look at normal conversation, so that we are not in normal conversation right now because I'm projecting my voice to fill the room, right? Normal conversation would be just you talking to your friends, right? Not shouting at each other, that kind of thing, right? Okay. And then a vacuum cleaner. So that's a difference of 10 decibels, and isn't it? So on a logarithmic scale, going from 60 decibels to 70 decibels, that represents a power of 10 difference in the intensity. So the vacuum cleaner isn't like it's 10 times more powerful than a spoken conversation. But the difference between normal conversation and busy traffic at 80 isn't 20 times, it's 100 times. So to go from 60 to 80 represents a 100 times difference in the intensity of sound. So it gets kind of tricky that way, right? So if we let's do some what ifs. Let's get a better color. Let's do, 20 to 30 decibels. How much more intense is the 30 decibel sound? 10. Okay. Let's go from 40 to 60 decibels. How many more times intense is it? 100, right? It's like you go 40 to 50, that's 10. And then 50 to 60, that's another 10. And so it's 10 times 10, which is 100. Okay. So what if we go from 20 to 50? It's 20, and then there's the 30, 40 to 50. 10 times 10 times 10 is 1,000, right? So that's where the problem with kind of the decibel scale lies. It makes it really nice and easy to like kind of reference sounds and their relative intensities, but like understanding like how much more powerful or intense a sound is, we can't just use our linear, it's 20 spaces away, so it must be 20. It's not. It's 100. So on and so forth. So just watch out for that. This is what happens when you go get an ear exam or an ear test, okay? This white area right here is the area which normal humans can hear. And when you get a hearing test, what they're trying to do is they're trying to map the size of this white area for your particular ears and brain. And so what this is trying to indicate is that like at really low frequencies, we actually need the sound to be much higher in its volume for us to perceive it. So we don't hear equally across all the frequencies that the human ear can hear. The human ear can hear down to about like 20 hertz, like the lowest bass notes that we can hear around 20, 30 hertz. We can feel bass notes below that. Like one of the purposes of a subwoofer isn't so much to give a low note as it is to give vibration, right? You can kind of feel it in your chest, okay? But in order for us to perceive those low frequencies, the sound needs to be pretty intense. And again, threshold of pain, 120 decibels, right? In a subwoofer, you can actually get that. You can hit the threshold of pain before you can actually hear the sound and cause damage. But as we get into like 1,000 hertz, right, we become very sensitive to the sound, right? So hearing loss isn't so much about like, well, you just can't hear a sound. at what frequency can you not hear the sound, right? Really matters. As you age, your ability to hear up here in the high frequency areas, the upper limit of human hearing and frequency range is about 20,000 hertz for a normal person. Younger people tend to be able to push that a little bit more and hear higher than 20,000 hertz sounds. When I was in college, there was this craze where teenagers would install these ringtones on their phones that supposedly their parents couldn't hear. Did you guys ever hear about this? They're like these high frequency ringtones. Your parents can't hear your phone ringing, blah, blah. This is back in the age of flip phones and stuff like that, right? And it was hilarious to me because they were selling these ringtones and they didn't work, of course, because cellular phone speakers were incapable of producing sounds above like 4,000 hertz, right? So the fact that they were selling them a high frequency ring, it didn't make any difference. Because old people like me, we tend to be able to hear like at least to 15,000 hertz, right? So your hearing loss, you start at 20 and you kind of come down to 15. Now, in my particular case, I had hearing damage and I can't hear anything above 14,000 hertz. That was starting around age 20. And I only discovered that when I was doing a demonstration at a physics show. And I had the speakers out and I was changing the frequencies. And we did this thing. Okay, keep your hand up if you can hear it. And I started turning the frequency up, right? And I stopped hearing it while the rest of the audience was like, right? And I just kept going, and then the hands kind of slowly, and then as soon as I passed like 23,000, all the hands were down. My hand was down at around 14,000. So I ran and got my hearing checked. Sure enough, can't hear high frequencies. My friends in computer services, because I used to work IT for the campus, they would always complain that the old-fashioned big monitors, like those really heavy, thick ones, they would complain that there was a high-frequency sound that would come out. I could never hear it. It's like, there's something wrong with that monitor, man. There's a sound coming out of it. I'm like, okay. It's like, are you hearing voices? Right. Okay, so that's the decibel scale. We've got to be able to work it. So let's do some examples, right, of kind of working your way through sound intensity and dealing with like these conversion formulas, right? They're a way of going back and forth. It's the Google Translate from decibels to watts per square meter, okay? This probably never happens. You're watching something on your computer or your phone or anything like that. And of course, nowadays, everybody's got their AirPods or whatever right in their ears, okay? But let's say you're just listening to something on the speakers on your device, okay? And the sound intensity is 50 decibels. And then somebody comes in and starts talking at you at a number that is 10 times higher than normal conversation. So I'm not going to judge, but some significant other in your life has come in and is yelling at you to get a life, get a job, do something, right? Okay? So what we're going to find is the total intensity of the two sounds together. The 50 decibels coming from your device and the 70 decibels coming from the person in the room. So, any guesses as to like what the new sound intensity is going to be? It's not, we can't add it, right? We know we can't add it. But I just want to see if you can guess like what the new intensity is going to be. Not that much higher than 70?
70 is 1,000 times higher than 50.
100 times higher than 50. 50 to 60, 60 to 70 is 2 tens, right? Okay. So the 70 decibel sound is 100 times louder than the 50 decibel sound. So it's going to kind of override it, right? Usually people guess 90, 100. Watch this. So to add these sounds together, what do we have to do? The only unit we can add is in what? Watts per square meter. So what we need to do is we need to find, not a laser. We need to find the intensity of the 50 decibel sound, and we need to find the intensity of the 70 decibel sound. We're going to do that by going back over here to our equations, right? We got two boxed equations over here that we can use. So let's take advantage of all the electrons that are here, and let's try to copy this. Oops, I moved it. Let's paste it over here, right? And we can get rid of all this stuff in between. I love electrons when they work, when they do my bidding, okay? All right, so there's our two equations. How are we going to find the intensity of the 50 decibel sound? Which of the boxes are we going to use, top or bottom box? Guess again. Bottom. We're looking for intensity in watts per square meter. We're looking for I. So we're going to put in I naught. Does anybody remember what I naught is?
1.10 times.
It's 1 times 10 to the minus 12 watts per square meter, okay? And then 10 to the 50 over 10, right? So it's 10 to the 5, okay? So this is going to be a number, and this number is going to be 1 times 10 to the minus 7 watts per square meter. How did I do that so fast? What's 10 to the minus 12 times 10 to the 5? What's the rule for exponents? You add them together, right? And what's negative 12 plus 5? Minus 7. That's how I was able to do that so fast. Because it was nice powers of 10. It isn't always nice powers of 10, by the way. Like if it's 55 decibels, then it's 10 to the 5.5. I have no idea what 10 to the 5.5 is. My calculator does. Right? But I can't do that one in my head. All right, and then the 70 decibel sound. 1 times 10 to the minus 12 watts per square meter. 10 to the 70 over 10, which is 10 to the 7. So this is 1 times 10 to the minus 5 watts per square meter. So now that I know the intensities in watts per square meter, I am now allowed to add the sounds together, because watts per square meter being a linear unit, you can just add it together, no problem, and away we go. So when you add these two together, just believe me, you end up with this. Yeah. Again, I added 1 times 10 to the minus 7, which is 0.01 times 10 to the minus 5, to 1 times 10 to the minus 5. Don't get too hung up. Just do it in your calculator. I'm just kind of flexing on my ability to count by 10 watts per square meter. Okay, and now we need to put this back. So we found the total intensity in watts per square meter. Now we've got to put this back into decibels to figure out like how loud is the sound, combined sound between the 50 and 70. So how do we get this back into decibels? Top equation, right? The decibel amount will be 10 log and then 1.01 times 10 to the minus 5 all over 1 times 10 to the minus 12. This I cannot do in my head. This I need my calculator for. Yeah, this turns out to be 70.04 decibels. Notice it's barely louder than the 70 decibel sound. So what happens to your attention? If you're listening to a 50 decibel sound and a 70 decibel sound comes along, what are you now hearing? The 70 decibel sound. You're not hearing the 50 decibel sound anymore. Okay? Because that 70 decibel sound was 100 times more intense than the 50 decibel sound. Okay? This is why advertisements, if you've ever been watching like YouTube or television or something like that, and the show transitions from the show to the ad break, what do they do to the volume? They increase the volume for the advertisement, right? You go from some cliffhanger moment in your show or whatever, right? And the person's about to die, and it's Edward and Jacob. I'm on Team Charlie, by the way. And then, okay, who was Charlie? He was the dad. I'm always on the dad side, okay? I remember my daughter asked me that, like, are you Team Jacob or Team? I was like, I'm on Team Charlie. She's like, so the big dramatic thing has happened, the dun-dun-dun moment, and then it switches, and it's like, hey, you want to buy a car over there, right? It's like, right? Why do they do that? To grab your attention. Because they know your physiology and your psychology are like, loud sound, what's going on? Flight or fight. Advertising, legal manipulation. Okay, I'll stop being political. Is that political or philosophical? Yeah, okay. All right, commercials should be illegal, just saying. Where was I? Oh, we did this problem. We're done, okay? So, let me, before I move on to the Doppler effect, I don't remember if I gave you a problem like this on the homework or not, so I'm just going to say it anyway. The decibel level, the intensity of a sound depends on how far away from that sound you are. The further away from the source of sound, the less intense it's going to be. So, if you're standing in front of a rock concert and you're hearing 100 decibels and you want that to go down, you just walk away from it and the intensity will go down. Why will the intensity go down if you change the distance? That R squared, right? You get yourself 3 times as far from that speaker and the intensity has gone down by 9 times on the watts per square meter scale, right? The thing that never changes when it comes to sound and sound output is the power. The power being put out by that sound source is the same whether you are microns away from it or miles away from it. So sometimes you'll have problems where they'll say a person is hearing a sound 100 decibels and they're standing 3 meters away from a speaker. How far away do they need to get in order to hear it at a more comfortable 50 decibels, right? The way you find that distance is find the power of the sound. If you know the intensity in watts per square meter, how do you find the power? Right? You can if you know the intensity in watts per square meter, and you know how far away something is from that source, you can find the power, right? Solve that equation for P. That power, that work per time, that energy per time will be identical for the new distance, okay? So that's the thing that stays the same no matter how far away from a source of sound you are. The amount of energy that that source is putting out per time is constant, stays the same. The intensity changes because we move further or closer away from that source of power. All right. Doppler effect. This is fun. I like this one. Okay. And I've got a demonstration of the Doppler effect right here. So we'll see what it is, or we'll hear what it is, and then we will talk about how to figure out what's going on. Okay. So what I've got here is I've got a kind of a football-shaped thing. I think you're supposed to like throw this between 2 people, but several students died. So we changed, okay? We changed how we did this, okay? So what I've got here is I've got it on the end of a string, okay? And assuming the string isn't broken, I should be able to swing it above my head like this. Now, the football is going to put out a sound, right? And what I want you to do is I want you to listen to how the sound changes as I swing this above my head. It's an annoying sound, but. Anybody going to give me $20 to turn it off? 30? The price just goes up. All right. So it's really annoying when it's just sitting there, right? Constant tone. But if I move it, do you hear how the tone changes? Right? What's it doing? It kind of goes high-pitched and then low-pitched, right? Wee, wee, a little bit like a siren kind of thing, okay? What you just heard was the Doppler effect, okay? The Doppler effect is the shift in frequency of a sound when it moves towards or away from the person doing the listening. I forgot to load these up. Give me a second. These are animations, and these animations are pretty important. So let's take the time to get this right. Where is it? What chapter are we in? 16? Only sometimes, right? Okay. Let's go to this one. Hit play and make sure that you guys can see what's going on. I thought there were no videos or animations. I was wrong. Okay. Choose content, mirror that one, go here. All right. Sorry about that. I just wasn't ready. Okay. So what we're going to do, we're going to play the, okay. So this is kind of what sound looks like when a source, like a trumpet, is just emitting that sound and a person's just sitting still, like at a normal like concert or something like that, right? And in that animation, I hope you saw how the rings spread out, right? This, again, modeling sound as these waves coming out from that single source. And these waves look fine. Nothing's changing. Nothing's, it's all normal, all that kind of stuff. So this next animation is with the trumpet moving. Okay? So the trumpet is moving towards the person. Think of somebody playing a trumpet while like on a car or something, right? Okay? And they're moving along. What happened to the space between wave fronts right here compared to behind? They got smaller, didn't they? Like because the trumpet was moving, it compressed the wave fronts, the wavelength got smaller in front than it did behind where it got stretched out. This is the Doppler effect. It's this acknowledgement that a moving source of sound will cause the sound waves in the forward direction to squish together and in the backwards direction spread apart. Now, if the wavelength gets smaller, what happens to the frequency? It goes up. Okay, when wavelength goes down, frequency goes up. Remember, speed is determined by the medium in which sound travels. So if wavelength changes, frequency does the opposite change. So if the wavelength gets smaller, shorter, closer together, then the frequency is going to go up. It's going to get higher. And so this person would hear the trumpet's note as being higher than it actually is. And if they were standing behind the trumpet, and the trumpet were moving away from them, what would they hear? They would hear a lower note, right, than than the sound is actually emitting. This one's really hard for people around here to imagine, but let's just imagine there's a train track, okay? And the trains go up and down it several times a day, right? So when that train is blowing its horn, right, and it's coming towards you, you hear a much higher pitched horn than after it passes. Now, of course, speed matters, right? And so if it's one of the freight trains, it's not much of a difference. But if one of the passenger trains, you can kind of really hear the difference there, right? Because passenger train's moving much faster. And this is another one that's kind of hard for people at Fresno City College to come to grips with. Let's just say that there's some cars on campus that have trouble with their mufflers. You go out to Blackstone or McKinley or something, and you see those cars, and like, you know what I'm talking about, right? Okay. By the way, you have to practice that for months to get that. Why was that car's engine sound so much higher as it came towards you and then shifted to the lower band? It's the Doppler effect, right? You have this, it's coming towards you, it's higher pitched, and then as soon as it passes you and starts moving away, it's lower pitched. So what we want to try to do is capture mathematically how to, calculate what those shifts in frequency are, right? And be able to figure this out for all cases and that sort of thing. I used to fly like drones and model airplanes and all that kind of stuff. And one of the ways that we would measure the speed that one of our model aircraft was moving at is to have the pilot fly past us while we held microphones, and we would measure the frequency shift in the sound of the engine of the aircraft. And by getting the high and low frequency, the Doppler shift, we could tell you how fast the plane was moving. Really quick way to figure that out. Nowadays, you just put a GPS receiver on the drone and you're done. But back in the day when we did it the hard way, walking uphill both ways in the snow. I know, I sound like an old man sometimes. What I'm not going to sound like an old man now is I'm going to tell you to ignore the book. I know usually this is not a piece of advice that a teacher would give, right? Okay, read the book, all that kind of stuff. This time, for whatever reason, physics textbooks make this too darn hard. I don't understand why they feel this compulsion to make it so difficult, okay? Because it really isn't that hard. And so I'm going to show you the Mr. Balogh method for surviving the Doppler effect, okay? Surviving calculations with the Doppler effect. So what a lot of textbooks do is give you many equations. 2, 4, 8 equations for various situations. It's too many. There is one equation to rule them all, and in the darkness bind them in the land of Mordor where the shadows lie. Just one. You have to be careful about what signs you put on things. So either do the book's way and have like 16,000 different equations for what's going on, or do my way where all you have to do is be careful with signs. You can pick, but this is the Mr. Balogh method for doing the Doppler effect. The one equation, the frequency heard by the observer is equal to the frequency of the source times V plus V observer all over V minus V source. There's your one equation. It's the only one you need. To be able to pull it off correctly, though, you need to be careful about the positive and negative signs you put on V observer and V source. The V all by itself is the speed of sound in air. Okay? V observer, V source. And what I do, because I'm like a visual learner and I just like to see it like visually organized, what I do is a little tiny spreadsheet. Looks like this, okay? What I do is I do V observer, V source, and then I go towards and away. And in the towards column, I put pluses, and in the away column, I put minuses. Now, you, of course, are probably smarter than me and can remember something if I just say it to you, but I can't remember things that are ever said to me. So the simple version of this is towards. If anything's moving towards something else, it's positive. And if it's moving away, it's negative. It's just, for me, having that little spreadsheet right next to the equation helps lock me in. This is my anti-dyslexia methodology, right? So that's what I do. You'll see me kind of draw that little thing off to the side every once in a while when I'm solving one of these problems. So what does that mean? It means that I can handle any situation involving the Doppler effect with just this equation and getting the directions correct. It's like a little tiny bit of vectors in here, but not really. It's not. So let's do some examples. There's the equation, Mr. Balogh's. I mean, it's not my equation. Doppler wrote it down, but like different from the way your textbook is going to present it. So I'm going to do 4 problems in one. So I wrote this problem to just as a way to show you how to work through the Doppler effect. There's four possibilities in the Doppler effect. And by the way, we're doing one-dimensional Doppler effect, so we're not worried about 2 dimensions or 3 dimensions. Just It's just basically objects moving along a line towards or away from each other. So in the case of an ambulance, you're driving along some road somewhere, maybe it's Highway 41 something, okay? And an ambulance is near you. There's only 4 situations that can exist for the Doppler effect to have happened. And so I'm gonna get all these down here, okay? We'll do A, B, C, and D, okay? We'll do them in different colors. So let's just, for sake of argument, let's just say you are traveling northbound, okay, at 25 meters per second. And we're going to do that for all the cases. We're not going to change the direction we are going, okay? What could the ambulance be doing? Like, where could it be and what direction could it be going? Like, there's 2 choices for where it could be. If you're going this way, where can the ambulance be? Either in front of you or behind you, right? Okay, so there's only 2 choices for where it can be. And then there's only 2 more choices for what direction it could be going. So if it's in front of you, it could be coming towards you in the opposite direction. Or, what could it be doing? Going away from you, but in front of you, right? Same thing behind, right? It can either be going away from you, behind you, or catching up from behind, right? That's it. Those are the 4 possibilities for what can be going. You're like, but Mr. Balogh, what if you're going that way? Okay, fine. I'm going this way, and now it's coming. They're all the same. It's the same set of conditions. It's just we changed the directions on you. Okay, so let's write them all down. I'm going to go with the ambulance is in front of you and coming towards you for A. For case B, what did I do? I did. So you're going the same way, but now it's past you and is behind you, moving away from you. Okay. For C, what did I do? I did. We are moving upwards, and the ambulance is coming up behind us. And then finally, the last one, we'll do in green, case D, where we're still moving northward, but now the ambulance has passed us, right? So those are the 4 cases. And again, you could turn this sideways, left or right, up or down, right? You're only ever going to have 4 cases. This is all of them, okay? So let's calculate for case A, right, what we would hear driving in our car with an ambulance coming towards us, okay? Frequency of the source. What's the frequency of the source? 2500. And then we're going to do V plus V observer all over V minus V source. Okay, so frequency of the source, 2500. Speed of sound in air. If you're not told, what do? 343. What I do is I write 343 plus, and then on the bottom I write 343 minus, and then I put in some more parentheses because it's the only way I can keep things straight. What is the speed of the observer? How fast are we going? We're going 25. But are we moving towards or away from the source of sound? What does the word towards mean? Like it means oriented in the forward direction at something else, right? So look at what's going on here, right? Our direction is pointing to where the source is located. We are moving towards it, right? And so based on the little, what is it, V observer, V source, towards and away, right? Towards is positive, away is negative. What are we going to put in for that top number? Sign and magnitude. What are we going to put in? Positive 25. And what about the source? What is the source trying to do? Is the source more moving towards or away from the observer? It's moving towards. Look at where the direction is pointed, right? It's pointed towards or in the direction getting closer to the observer, right? So what are we going to put in for that number? Positive 40. And then we're going to run the calculation. I did this already. 3,040 hertz. And we're going to stop and we're going to check. The source and the observer are coming towards each other. Do we expect them to hear a higher or lower frequency sound? Higher, right? In our experience, or like what we talked about in our examples, right? If they're coming towards, we should hear higher. Is 3,040 higher than 2,500? Yes. My number may not be right, but at least the concept is. Okay. Now, with the ambulance past us in case B in the red here on my screen, okay, we're going to calculate the frequency of the observer here. I'm not going to write the equation down anymore. 2,500, 343 plus parentheses, 343 minus parentheses. Again, it's like the template, right? And the only real hard part now is figuring out if it's towards or away and getting the signs correct. The observer. What is the observer doing now? Moving towards or away from the source? Away. The vector is pointed like away. I don't know. I don't have any words. So if it's away, what are we going to put up there? Negative 25. And what are we going to put on the bottom? Is the source moving towards or away? Moving away. So negative 40. And then when I go to calculate this, I got 2,080 hertz. Is that lower or higher than the original sound? That's lower. And again, does that jive with our experience? Yeah, right? If the train is past you, you hear a lower sound, right? Okay. Let's do case C. Okay, we're getting a little bit tricky now. We're still going to do the standard template. Plus parentheses, 343 minus parentheses. That always stays, right? The 2,500 is going to be different whatever problem you're in, right? And maybe they're going to be stupid and say, the speed of sound is 295. I don't know. Okay? Just put that number in, right? But if they don't tell you the speed of sound, 343. Okay. Is the observer moving towards or away from the source? Away. This is away. Now, don't clue in to what's happening, they're getting closer to each other. Don't worry, the math's going to figure that out. What you need to look at is see which direction the observer is going compared to the source, right? And it depends on where the source is too, right? Because here the observer is trying to get away from the source. They're not doing it because the source is moving faster, but they are moving in a direction away. But now, in the green one, now what direction is the observer going? Towards, right? And that all changed based on where the ambulance was. Okay, so if the observer is moving away, that's a minus 25. What is the source doing here? It's moving towards. Okay, so what are we going to put in? Positive 40. When I did that one, I got 2,620. Okay, now this is pretty interesting. First of all, is it higher or lower than the source? It's higher. 2,600 is higher than 2,500. But it's not as high as case A. Why is it not as high as case A? If you're moving at 25 and the ambulance is in the opposite direction in front of you, coming towards you, what is the relative speed between the car and the ambulance? It's 65 meters per second. Okay? They're approaching each other at 65 meters per second. But if you look at the blue one, okay, what's the relative speed between these two? You've got 25 forward, you got 40 catching up behind. The relative speed's now 15, isn't it? Okay? So the Doppler effect equation can handle all of the relative velocities between these objects, no problem. You don't have to think about it. What do you have to think about? Towards or away. Towards or away, that's it. Okay? So if you get that correct, you'll get the rest of it right. All right, let's do the last one. Half observe, 2,500, 343 plus, 343 minus. Okay, we already figured out the observer was moving towards, right? Plus 25. What's the source doing? It's moving away, isn't it? Okay, so negative 40. And this gets me to 2,400 hertz. So again, lower because they're getting further apart from each other, but not nearly as fast as if the ambulance had passed going the opposite direction. That's basically like kind of all the Doppler effect equation problems we can do. Of course, physics textbooks will try their very hardest to be as hard as possible, right, and asking the questions. So it could be possible that you are given like the frequency that the observer hears and the frequency of the source and are asked to find the velocity. So what's going on there is you've got to solve the problem for v, which means you got a lot of algebra to do, right? Okay? So I'm just kind of warning you that that's often what homework and that kind of stuff will do to you. They'll make the problems mathematically difficult. I wouldn't really do that to you on the exam. Because you don't have time to do a bunch of math. There's also like horrible situations where they will like not tell you the frequency of the source. They'll just tell you how much the sound shifted. Okay? So like for example, they'll say that there was a 540 hertz difference between the sounds. Right? So like I'm looking at the black, 2,500 and 3,040. The Doppler shift, the amount of shift in the frequencies, is 540 hertz. Knowing that shift, you can work backwards to the velocities between things, right? But that means having to set up like two equations and solve for two unknowns. So I don't want you to get lulled into a false sense of, oh, well, there's only 4 problems and we've done all 4. Mathematically, you can be forced to like find some pretty horrible things, right? But really, there's only one equation that you have to deal with. This equation, by the way, handles for things that are standing still. What do you put in for the velocity of the observer if they're just standing on the side of the road? Just put 0 in, right? You don't have to worry about it, okay? As well as the opposite, okay? What if the train is oh, hello, train. What if the train is standing still on the tracks and you're walking towards or away from it? What would you put in for the velocity of the source? 0, and then, right, you're moving towards or away. So this works for all those cases, right? What if two things are moving at the same speed? There's no change, right? So if they're both 0 or you're both going 100 miles an hour in the same direction, there will be no Doppler shift perceived between those things. All right. I think. Oh, we got to talk about this. That's right. Oops. What happens when you? I'll come back. What happens when you do like the extreme of the Doppler shift? Okay. So this is a Navy fighter, FA-18 Hornet, that is breaking the sound barrier. Okay. It's doing it in a location where there's a lot of moisture in the atmosphere, which is why we're seeing the Mach cone form over this one. This is an area of really high compression, and so it condenses the water molecules real suddenly. But this is kind of what a sonic boom looks like in a sense. What's going on here is, and this is a, can't believe I still use this animation, but it's fun. Let's go to right here. This wasn't made by me. I kind of wish I had made it, okay? because it's Windows versus Apple. Okay. But we got this little animation here of a plane moving along, okay? And it knocks the window out of the window and knocks the apple out of the tree. Okay, fine. That plane is moving faster than the speed of sound. So when you push and you take the Doppler effect and you push it beyond like its extremes, okay? And you have a source of sound that's moving faster through the air than sound can move through the air, you end up with what we call the Mach cone. Do you see how all of the wave fronts are kind of piled up on top of each other? Compared to the trumpet picture I showed you before, where all the waves were nice and separated from each other, this one, right, those waves, they're like kind of adding up all along one line, right? That line is the sonic boom that you hear when, like, say, a plane flies over going faster than the speed of sound. It's a boom because you hear none of the sound and then all of the sound waves hitting simultaneously. It's a bam, right? It like rattles things and it shakes things depending on how close you are to it. So where do you want to be looking if you hear a sonic boom? Most people hear a sonic boom, they think the world's ending and they get on TikTok and they do that. But like, where do you look? You don't look up. Look at the angle of the Mach cone. If you're standing right here and you look straight up, you won't see the airplane. You have to look sort of sideways, 360 degrees around you to find out where because the plane's not here, plane's over there somewhere, right? Okay? So as soon as you hear the boom, don't look up, go like, look for where that plane was, okay? I used to go out and watch when the space shuttle would land at Edwards Air Force Base. They only did it a few times, but I remember going out and my family dragged, my uncle and aunt used to live down in Lancaster. And we'd go out and the space shuttle enters the atmosphere at like Mach 25 times the speed of sound, and it has to slow down to 0 by the time it lands, right? So with every multiple of the speed of sound, you get a new boom. Now at Mach 25 on atmospheric interface, there isn't really enough air there for the sound to carry, but as it came from like Mach 7, 6, 5, 4, 3, 2, 1, you could hear booms for each one of those. So you'd be sitting out there, boom, and then like 20 seconds later, boom, and then another one, boom, right? It's pretty fun. You can hear it at rocket launches and all that kind of stuff too. So this angle that is formed by the Mach cone is indicative of like how fast the thing is going. Oh, by the way, Mach numbers is a ratio to the speed of sound. So Mach 1 means you're moving the same speed as the speed of sound. Mach 2 means you're going twice as fast as the speed of sound, so on and so forth. What do you think pilots hear in the plane when they go through the speed of sound? It's not that they don't hear nothing, they just hear what's going on around them. They don't hear a boom because where's the boom? Behind them, right? Okay, right? So, but are they able to hear the sounds in the cockpit if they're going faster than the speed of sound? Well, yeah, because the cockpit is moving at 0 relative speed. Well, you hope that the cockpit is moving at 0 relative speed to you if you're the pilot, right? So there's no like, the speed of sound, whatever, right? Just because they're going faster than the speed of sound doesn't mean they lose all their hearing or something, okay? Now, this image that you see here of this Mach cone should be, you've seen it before, just in a different medium. Where have you seen this before, not in air? It's a situation where the source of a wave is moving faster than the wave can move through the medium. What's a wake? It's another name for a funeral party. No. That got dark real quick. A wake is that V-shaped pattern that forms behind a boat when the boat does what? Moves faster through the water then waves can travel in water. It forms a wake, the wake being the place where all the waves that are coming off the hull of the boat are peaking at the same time, cresting at the same time. And so then you tie a rope onto the back of the boat, you throw a board in the water, and you wakeboard. Right? They're literally surfing on the boom, right? Not a sonic boom, but the place where all the water waves are happening at the same time. I finished chapter 16. Right? Oh, you don't clap, don't clap, don't clap, because it's better when I go slower, right? So that's chapter 16 done. What's happening tomorrow? I realized I didn't check. Do we have a lab? Yeah, you don't have the handouts, do you?
No.
Because I haven't picked them up yet. Physics. What is this class? 2A.
Yeah.
It says, okay. It says lab, lecture, and problem solving. I'm just looking at So I need 2 days for chapter 17. That starts tomorrow. Okay? So our lab tomorrow is going to be an hour and 15 minutes of lecture. Okay? Followed by the rest of the time you can get help on your homework or whatever. Okay? So tomorrow's lab is lecture. So come, we won't be doing like a lab thing. We are going to do our lab for sound and standing waves next week after I teach. I'll start teaching you tomorrow about standing waves. Okay? So that's what's going on. Don't miss it.